Okay. So this section is going to be talking about how to take derivatives of inverse functions and how they relate to the original functions when we take a derivative. There's a couple different reasons we want to look at this. The most important inverse functions, calculus-wise, are going to turn out to be inverse trig functions, but this will work for all types of inverse functions, as it turns out. So this picture, which comes from your text, is a really good way of seeing how inverse functions and their derivatives relate to it. So if you remember, let's say this blue line here is my original function f of x. So if we want to draw the inverse function, how would we know how to draw that? So the picture says, go ahead.
I guess one way would be thinking about it as that reflection across y equals x, right? Because when I usually think about like an inverse, we think about swapping x and y and then trying to solve for y. You can't always do that. Like you said, for inverse trig, that might be difficult. But that seems to be what's happening here, right? It's reflected across x equals y.
Right, so we have this other line, other curve, sorry, at the bottom of it. And what we're really interested in this case, when we talk about a derivative, remember that's the slope of a tangent line at a point. So if we say like, oh, I want to find it at x equals a, you draw the line, you find the slope, and it's p over q. Well, that's very good, but that assumes you know everything about the about the inverse function. Mm-hmm. So that means maybe we need to use that same rule that you were talking about with the original function and how its derivative compares to it.
Mm-hmm. So I can see there that it looks like that triangle they're taking with the p and q sides, that when you reflect it, right, it also seems like the tangent line is getting reflected and is becoming the tangent line of the original function. So if you know something about the tangent line of the original function, it could help us find the tangent line of the inverse function.
Right. So then the question comes like, well, if you're reflecting it about, how does that reflect in terms of the actual values? Mm-hmm. Well, if we're saying the slope of the inverse function at the tangent line is p over q, if we sort of switch the x's and the y's, remember slope is rise over run. The rise is the change in y. The q is the denominator is the change in x. That's the run. Well, if you're reflecting the x and y, you're changing their roles. So what was in the numerator is now the denominator. What was the denominator is now the numerator. Mm-hmm. And that actually shows up when you look at the triangles, when they're reflected. The vertical one was q. It's now that p value. And the other ones are also flipped. So that means is the slopes are the reciprocals of each other when you look at it. Now, there is that thing like, why am I coming up with why are they have these points, a and f inverse of a and all that sort of thing? How do we know that works? Well, the points are reflected as well. So originally we said, I want to know the tangent line at a. Well, the value of the inverse function is f inverse a. And when you reflect it about y equals x, that is also reflected. So then the problem is, okay, we have all these things, everything's reflected. How do we make that into a nice little formula for it though? If we know the slopes are reflected, well, that means that something about the derivatives, those also have to be reflected.
Yeah.
So for at a, we know that 1 over the derivative of the original function has to equal the derivative of the inverse, but you just have to be careful where you're taking the values. The original function you take at f inverse of a, while the slope of the inverse has to be at a.
Yeah, and I think to me that's the most confusing part. I mean, there's a lot going on in this picture. Yeah, but the fact is that a, for the inverse, that's what you're plugging in. So a is like an x value. But if you look at the original function and you look at the input value, right, on the left side, the input value is f inverse of a, because for the original function, a is kind of representing y. It's like the output, right? So f inverse a is what gets plugged in to that function f prime, right? So it's f prime of F inverse A. And to me, that's part of the part that's confusing, but I think why this is such a powerful picture.
Right. I agree. And the idea is it really doesn't matter which A, as long as it's in the domain of F inverse, it can really be anything. So that's why we can have the general formula for the F inverse right down here. So it's kind of nice that we have a nice little general formula down here, or not so little, I guess.
It could be worse. I mean, quotient rule looks a lot worse for sure.
Okay, that's true. I agree with that. I know quotient rule pretty well. You know,
Yeah.
it took effort, but I know it. One of the critical things I said at the beginning that this works for all the inverse trig functions as well can do this. They have their formulas, but if you forget it, you probably do know, hopefully, the formulas for sine and cosine and tangent and so on like that. And so this is kind of like a backup way of doing it. It's a way to prove that it works for inverse trig, but it's also a way, if you forget those and you remember the regular trig, this is a way to sort of keep it in the back of your head.
To rederive them.
Rederive them, yes.